My name is Josh Marshall. I work at UStudio. I get to work with great folks like Tim, and we are actually hiring, so come by our booth if you're interested in, we do a lot of things in Python, Kubernetes, all those kind of things, so come talk to us. I have a history of working with a lot of different network-oriented services, event-driven things, so that's why Coroutines, this sort of talk is exciting for me to give. And there's my Twitter and GitHub if you're interested. So here's the rough agenda, what I'm going to try to make it my way through. First is what are coroutines. Second is why should we care? Why do they really matter? Why is there so much activity around it right now? How have they evolved in Python? That's going to be the bulk of the conversation, just going through how coroutines have been implemented over the years, and then a little bit of what's next and closing thoughts. So a bit of caveats. This is from a user's perspective. I have not worked on the PEPs myself. I have not submitted anything to core Python. This is just I've been using a lot of these tools and services over the last 10, 15 years. So I'm just going to give you sort of an overview from my own experience as I've moved through libraries. It's going to be, because there's a decent chunk of content, it's going to be informal, and I'm going to be simplifying some things, so leaky abstractions lie ahead. And again, when you talk about things like coroutines and generators and network services and sockets and all those kind of things, there are a lot of rabbit holes, and we've got a little bit of limited time. So come grab me afterwards if you have any questions, if you want to go deeper. If I say anything incorrect, I love to be corrected. So come tell me about that later. So first, what is a coroutine? And actually, before I do that, raise your hand if you feel really confident that you know what a coroutine is. Okay. So I will be a little bit brief. I feel really confident. I saw a lot of this. So coroutines is a simple definition, but a method of cooperative multitasking, allowing execution to be explicitly suspended and resumed. Now this can take a lot of different forms, but essentially the key points there are cooperative multitasking versus preemptive multitasking, meaning you are explicitly saying, okay, I'm waiting on something, somebody else can run now. And in some coroutine implementations, that means you're telling the next person, go resume whatever you're doing before. In other cases, you're passing back to an event loop like Tim was just talking about and saying, I don't necessarily know who's talking next, but somebody else can go and do the next thing they need to. But the explicit suspension and resuming function is a core piece of it. Because of that, coroutines also provide an alternate way of reasoning about concurrent operations. And what that means is we come to it from a subroutine model. We come to it from like a blocking function approach. And a lot of times that works really well for a lot of different problem sets. But when you're talking about network operations happening in concurrent operations, in some cases in parallel across distributed machines, you need a different way of approaching the problem. When you're trying to make the code manageable, extensible, grow over time as you have changing business requirements and other things. So I like this quote because this is actually from The Art of Programming, the volume 1. So it's like, I don't even remember, like the 60s when this was first published. But Donald Knuth classifies subroutines actually as a special case of coroutines, meaning if coroutines can be entered multiple times, suspended and resumed multiple times, then that means a subroutine is just a coroutine that's only entered once and then exits with the return, right? So you're actually already thinking of coroutines, so it's going to be simple. So to cover a couple of points there, it's cooperative. You got to work together. That means if you block in one coroutine, then some other coroutine can't run. So you got to be thinking about that. It's concurrent versus parallel. So these are tasks running concurrently, but again, not running in parallel. And explicit, especially with what I'm going to talk through in Python, there are definitely some implicit coroutine implementations depending on the language and environment, but mostly what I'm talking about today is the explicit sort of coroutines. So there's a lot of other different ways you can classify coroutines, symmetric versus asymmetric, and a bunch of other things. Largely, we're talking about stackful asymmetric coroutines today, but if you're interested into diving into different implementations, there's a lot there. So why should you care? All right, that's great. It's a different way of thinking about things. Why does this matter? And Tim gave a pretty quick overview of it, and I'm just going to reiterate a couple of those points. Rise of network-connected services, as we're all building internet-enabled services, means that at least at some layer we're worried about optimizing for I/O versus necessarily optimizing for the compute resources. And so that means you have this accept, read, write problem, right? You need to be able to support as many simultaneous clients on your hardware as you can, right? You want to be efficient with the use of your machine. And essentially the C10K problem, which has been sort of like reworded as the C1 million problem, is can I take one machine and support 10,000 current clients or a million concurrent clients if largely what I'm doing is waiting on database changes or notifications or those kind of things. That's the problem you want to solve there to be efficient with your hardware. And so over the last 10 years, you see a rise. This is just the search query for asynchronous, and you can see there's just a steady increase in people looking for asynchronous solutions to programming problems. So with asynchronous libraries, coroutines, as you saw with Tim's example, can simplify that event-driven logic in that in the best worlds, it puts it into what we normally think about when we're looking at blocking functions. It functions the same way, and I'll show you some examples on how it changes over time. And again, coroutines can help reduce bugs because they encapsulate the logic of whatever task you're working on, as opposed to in callback structures or other things where that logic can be spread all over the place, and it can be very difficult to refactor and other things. So, an addendum to the why should I care, right? It's like, great, Josh, you're telling me coroutines are good. Why do I care about learning about all the way back to iterators and generators in the history? And so for me personally, I view that if we don't study the past, we're going to go and re-implement it, right? Reinvent the wheel, and we're probably going to do it badly. We're not going to understand the context. We're not going to understand the mechanisms that people went through before. And I just also like to understand the history, where it came from. I like to see who did what and why these things worked in different environments, because you don't always have the greatest tools in front of you. You might have to work in an older Python environment for some embedded device, or you might even be in another language, and you can take the lessons learned from Python's coroutine journey and apply it inside of a completely different language, completely different environment. So now we're going to talk about the evolution of Python coroutines. And I'm going to try to do it with a specific use case. So I'm going to go through this. Now, a little bit of a caveat to it is it's kind of fun. This is the standard demo challenge, right? You want to introduce a use case that is simple enough that in 45 minutes we can all sort of grok it and work through it, but sophisticated enough that it exhibits the challenges that we're trying to solve. And these aren't straightforward, simple challenges always, right? There's a reason it took a while to evolve some of these things. So the example I'm using is a TCP-based service. We're not doing HTTP server here. We're doing just JSON RPC over TCP connection. And that means it can be bidirectional. That means that you're not necessarily in a request-response cycle. You know, you might be sending in heartbeat indicators, or you might be sending in notifications, or the server may be sending you notifications, not necessarily in response to something you asked it to do. So that gives us a little bit of a fun workflow, because you've got reads and writes happening simultaneously, in response, delayed, whatever. So it's an interesting problem, but it's fairly simple here. And then you want to put it into a framework where eventually you can talk to other services. Now, I'm not going to show a lot of that today, but like Tim was showing you, you might want to talk to a database, or you might want to talk to Redis, or you might want to talk to some external HTTP-based service, and your server needs to have the capacity to do that, and you need to be able to scale with those IO-bound operations. So the simple protocol, we're not going to go too deep into this, but what you're going to see in some of the examples is we're tossing JSON RPC packets, and it's just 4-byte length integer and a message that is that long. So super simple protocol, not a real one. Don't go put this into production, use something real, but it's simple to conceptually think about. Also, huge caveat, anybody out there who writes TCP servers and that kind of stuff all the time, do not judge this code. This has been very, very clean. Like, I'm not handling reconnects, I'm not handling close, I'm not handling even like read timeouts. This has got no error correction, no protocol error corrections, just so we can talk about the nature of the code versus necessarily all of the details. And it's already going to be a little bit hard, I think. Hopefully the folks in the back can see. There's actually a screen back there, I'm realizing, so you can, it's a little bit easier to see some of the code examples. But this is a simple blocking version that those of you who write servers are going to immediately see problems with. Because it's blocking, and inside of a blocking function, it's very easy for any of us to sort of grok the code, right? The order it flows in, while true, okay, great, this is going to run forever because I don't see a break statement. Fine. But what this, if you're not used to writing servers and things, you're going to see that we accept a client connection here, and we haven't set our socket up for non-blocking. So then we while true with that client. Now, this client connection could be open for any period of time, writing, reading, waiting for all those things, but this server will only ever serve one client at a time, right? That's terrible. So then the client example is pretty straightforward. I'm just going to use this same client for all the examples, but it just connects to a service, it sends a connect message, and then it stays connected because it wants to know what are the changes coming from the server and other things. And so it just reads the JSON RPC packets, and it sends every 5 seconds a heartbeat back to keep the connection open and let it know the client is alive. So by definition, these clients are going to stay connected forever. That previous server only handles one client at a time. We have a problem here. So I actually talked through most of that. Also, it's the request response pattern here, right? It fires in it's reading and then it's responding is what the server is doing, as opposed to reading and writing simultaneously in two different coroutines. So you're breaking a little bit of the pattern. So what are the options to solve the concurrent clients and operations when you just jump into the problem? And a lot of folks, they'll immediately jump into threads. And that's fine. You're probably not going to take nearly as much advantage of the system as you can, but you're also going to introduce all the complexities that we know and love about threading. And so it's not necessarily the best solution to it. And that's why we're talking about alternate things. So we're not going to use threads. We're not going to use processes. Generally, what the recommended solution is, you're going to use an evented system like epoll, KQ, some of the wrappers around those like libuv, libev. How many people are familiar with those? Okay, a few folks. Basically, from a concept perspective, they all function the same way. You hand it a list of file descriptors or things to wait on, and you say, I want to know when X happens, when this file descriptor is ready for a read, or when this file descriptor is ready for a write. And so it's all callback oriented, right? Event driven again. And so all of them function in different ways, and they're all on different platforms, but that's the basic concept you come to them with. And so what that does is it gives you a nice, usually platform, part of the platform, part of Linux, part of Mac OS X, whatever. It gives you something to tie into to take advantage of those events, but now we have to put a programming model around it. And so you're largely managing callbacks on events. Now, a lot of you, if you've been doing asynchronous programming in JavaScript or even in some of the other frameworks and libraries, you are probably familiar with doing asynchronous development and callbacks and all the challenges those can present. But I'm going to start there because callbacks are pretty much supported in every language. You're passing this. First off, don't worry about trying to read all this. The whole point is that there's a lot of code because now we're dealing with callbacks. There's a lot of individual methods, and this is, again, not sanitized, not a functioning server for anything other than a demo case anyway. And the main things I'm going to call out are, one, you got all those extra callback functions. Two, we are non-blocking on the server now, so all socket operations, we need to have the server let us know when those are ready. And then we're adding these file descriptors and responding with callbacks when the right thing happens. So the first one is we take our server socket, we're on a port, on an IP, on a host, and we say anytime that server socket has a read availability, that means we got a new client. So then we come into the open callback. And then, assuming that this client works, I'm not doing any error detection here, but then I'm going to say anytime that client is available for read, pass to the read callback. Anytime there's a write available, pass to the write. So the callback-oriented one now does bidirectional read and write, and it handles a large number of clients. But we are now we're dealing with a very, very unmaintainable set of code as it grows. And you can lose stack context, and when callbacks aren't called like you expect them to, the system fails silently, and a client's stuck hanging or closes unexpectedly. Callback code is harder to reason about, and happy to debate that, but I think that's a generally accepted rule, and I've been doing callback code for a long time, and I still think that there's some challenges to it. So now let's talk about Python and how it improves on this and how it's improved on it over time. The first thing I'm going to start with are iterators. I'm not going to actually make a coroutine system with iterators, but they are an important stepping stone as you're moving through generators and ultimately to coroutines. So back in 2001, PEP 234, they added an iterator interface, which is essentially the next interface we all know and love. What this means is you can implement your own object that you can iterate over, get the values back, and you implement that easily with a class or in any sort of object definition. You define this iter method, you return something that implements the next method, and you're good to go. And so now you can use those kind of objects inside of list comprehensions and for in expressions and map and filter and a bunch of cool things like that. And so you can start with that, and that helps people start thinking about, okay, I've got this thing that I can turn this into a coroutine if I manage all of my state around re-entering it, right? You can build some really complicated but coroutine-like functionality with an iterator. So iterators themselves don't solve that problem, but you can like build a whole bunch of stuff to do that. Meanwhile, simultaneously while this is happening, stackless Python came out. Who's worked with stackless Python? A few folks. Okay. Stackless Python is really fun because it actually, it's an alternate, it took Python code, forked it a little bit, and introduced coroutines straight in. And if you've worked with Go or any of these other languages, it's kind of interesting to see something that from like 2001, they have these channels, they pass in, the channels are available inside of these individual coroutines. They are explicitly passing to each other inside of it, and then you set them up. They're called tasklets here, but they're essentially coroutines. And then you say, go run, and it works. This is 2001 or 2, I think, when it was added to stackless. This example was from 2006. So these concepts have been with us for a long time. But building on top of iterators, now we have generators. So great, you have these iterators, but we need a way to resume the context inside of the language as opposed to us having to build all of that context management inside of a custom iterator. And so I imagine you all have used generators. This is from the PEP 255 when they added it to Python 2.2. And this is what gives you your yield expression inside of functions. So you implement a function, you put a yield statement in there. The value after yield is returned to the caller. They can iterate. It's an implicit iterator. And when you call, it's not me. Okay. When you call next on the generator, because generators expose an iterator, then it will pick up immediately after that previous yield point. That's really important for coroutines, right? Because that means there's a lot of sort of stack and state management that happens in there, and then you don't have to worry about that. So you can use just pure generators that they launched to create coroutine-like workflows, and lots of folks did, but you're going to need trampolines, you're going to need different dispatch tools. And so I can show you like a slight version of the server that I showed you before. What happens when we start putting generators in there? And so now you can see the accept call. It listens for Mac's clients, but then it inside here we're yielding to see if a read is available on that socket, right? And so once that socket is available for a read, we know there's a client that we can accept. So now this is a little bit simpler than having yet another open callback and passing in those other kind of things. Now it's happening in this body, and we're just while true looping inside of the accept. Makes sense conceptually. Now we know this is the server running, waiting for clients, and that's all it does. Now we still call out to a handle client method. I'm not going to talk about that here, but we're still doing it with a generator, and we're yielding that out. And then what you can see here is what I'm implementing as the trampoline, because it doesn't come for free. All that we're getting with a generator is the value returned at an iterator, out of the iterator. But with these values, I can track these operation objects, is what I'm saying you would need to return here with the yield. And so you can track those operations. If it's a network call, if it's waiting on a file write or whatever it is, I can track those. Once the operation is finished, then I can call back into this this function, right? And you can stack those up. So it's not the most straightforward code, but it does already start looking a little bit more like blocking code. And you see that I'm actually not passing any values back into it. That's an important point for the next part. So meanwhile, while that's happening, Twisted launches. For those of you who have used Twisted callback oriented, but also introduces these concepts of deferred and sort of promises, brings it into the Tornado world over time. Greenlit, if you've ever used that, it merged from the stackless work and became like more of a package versus a fork of Python. But these are all evolutions that inform the coroutine implementation inside of Python. So now we're going to talk about enhanced generators. Remember I said a moment before that great, the generator can yield a value, but I need to be able to put values back into that context so that it can make decisions based on what happened as a result of that object. And I don't want to have to go make my own. So the PEP for that, here's the description of why that's an important concept, pretty much what I'm saying. They are almost coroutines in that you can pause execution to produce a value, but you do not provide a way for values, and just as importantly, exceptions to be introduced back into that context. So Python 2.5, they gave us generator objects that have, that they add the method to generator objects, send, throw, and close. So when you have a generator and you're iterating over it, you can now call .send and inject a value inside of it. You can call .throw and raise an exception inside of the body wherever it last left off that can be caught and responded to, or you can close the generator. And so now we've got the basic lightweight coroutines, right? And a lot of the asynchronous work since then in the Python 2 world has been built on these sort of concepts. So Tornado and some of these other ones, this is how, this was just coming out when I started using Tornado, way back in the day. So here is the most important line. You can see that yield on my receive call in the handle client code, right? I'm now assigning data, right? So I'm getting from whatever the receive code, I'm getting this data chunk back that's being injected back into the generator. And on the other side, here's just, I've got a little coroutine decorator. I don't actually show what that looks like, but it essentially does all the jobs of iterating, grabbing values when they're ready, sending them back into the generator context. But you can see, fairly straightforward now. I do have to decorate it to let it know that this is not just a normal generator. There's some magic values that I'm going to need to handle. But then I get, once again, a little bit more, it looks a little bit more like the blocking code, right, that we started with. Let's see. I forgot about this slide. I don't think I have time to go through this, but all this is on my GitHub repo for it, so I can share it. But if you're interested in how I implemented this little future concept, I wrote a little future implementation and a trampoline for bouncing those futures around. It's pretty straightforward and very buggy, I'm sure. So if you want to poke around in that. But we're still constrained to a caller-callee relationship structure for yield control, and that's important because now it's great. I have these generators that I can inject values and get values from. But then what happens if my generator needs to call generators, which happens all the time when you're talking about network services? My HTTP client may make a call, but then inside of the response to that, it needs to call to a database, or you need to chain these things. You need to have multiple options happening at the same time, and you need to be injecting exceptions all the way down wherever the actual call was last made, right? You don't want to have to write the boilerplate around every single generator stack. So we need some way of passing values all the way into a nested generator world, and we need the ability to grab values from way down in the depths. We need to do the same thing with exceptions, etc. So while this is all happening, this is where you have explosion of event frameworks. I say explosion, but there are a lot of them that came out. G-Event and Tornado are the two that I used the most in this period of time. So G-Event and EventLint are two that introduce monkey patching as a mechanism of putting some of these green threads and things in the implementations. And what that means is when you call a socket.receive, implicitly by importing G-Event, it overwrote that socket.receive, uses an internal event loop, does all of that without you having to know. Now the nice thing as a developer, great, you just import G-Event and all your socket code is magically asynchronous. And as we know, that never falls apart, always works great, right? There's no leaky abstractions. So I'm teasing it a little bit because I have my own personal perspective that I like explicitness when those things come in. G-Event was adopted by a lot of people, very, very successful in a lot of different ways. And so that definitely informs how we got where we are. But that's meanwhile. Also, Python 3 was released, and we all immediately adopted it. There were no transition problems. Everything's great. Subgenerator delegation is sort of the problem that I was talking about a minute ago, where you have these nested generators, and you need to delegate values or delegate control back further in the stack without having to write all the boilerplate around every stage of the generator. And so this is essentially PEP 380. They said the same thing. Delegate part of the operations to another generator further down the stack. It can only yield to its immediate caller is the problem. Let's delegate to further generators down the stack. This is yield from. This was introduced in Python 3.3. We also got the return statement inside of generators, which is kind of nice because we were building, I say we as a community, we're building some funny little ways of returning a value out of a generator that you're like iterating over, because you're yielding futures, and I need to let you know, no, this isn't a future, it's actually the value that's done. So we were raising exceptions as like raising a return value exception to tell the outer code that the function is done, which is does not make like immediate sense. You have to sort of learn to operate with exceptions as return values. So that's weird. And yield from solves that for us. Now we actually get a return statement, so you can return early whatever you need to. And yeah, exceptions are a saner. You get exceptions that make a little bit more sense. Your tracebacks and other things make a little bit more sense because you're able to inject those all the way down the generator sort of stack, and fewer trampolines. So while that's being released, async core was a async core was a library that was added to Python 2 something. I can't remember exactly which version, but that was an attempt to solve some of the many different loop implementations. And I didn't really talk about that before, but while you have this explosion of asynchronous and evented systems, they're all coming to it with their own flavor of event loop. You have to have an event loop. You have to have something that's managing all of these callbacks and futures and things like that, but they're each doing their own thing. So you'd have a tornado-based Redis driver that would not work with Twisted, that would not work with G-Event, that would not work with these other ones. So everybody's implementing the exact same thing in a slightly different flavor. Node.js came out 2009, I think, somewhere in this process. And so Node.js obviously is all callbacks. I think they've recently introduced some coroutine top-level concepts, but they then would bring promises and a bunch of other things into the JavaScript server-side world. And so that also very much informs Python, right, in that it's a competing environment in some cases. So I'm going to inject something here, which is we've been talking about the language, the elements of the language, but one of the modules that got shipped in Python 3.4, I believe, is async IO. This was PEP 3153 and 3156, and it's addressing this problem. Tornado, Twisted, G-Event, they're all doing essentially a lot of the same work on different event loops. We need a way to make these individual implementations portable across these different event loops, these different libraries and frameworks. A lot of duplicated effort. So how can Python, as a project, solve this? And so in 3156, they had been testing the Tulip project for a little while, and they brought it in as async IO. And that's the example that Tim was showing you before, that is now sort of the path forward for implementing different aspects of asynchronous programming inside of Python. So it was originally called Tulip. It was originally Guido's project. I say his project, but he was one of the main people driving it. It introduces a truly standard library inside of Python 3.4 again, I believe. And it's a familiar, and in many ways it was informed by Twisted and Tornado and other similar development because we've been doing that for a little while. And so it's pretty easy to hop over into. And it's a unifying direction for work moving forward. I'm going to talk a little bit more about this, but you saw even in Tim's presentation where he sort of patched out the base event loop to use the async IO. And he did that within Tornado. But Tornado and a bunch of the other ones have already done the work to say, we're standardizing on async IO as the event loop and allowing you to swap out. Your old code may be using Tornado's event loop. Now you can use the async IO event loop. That was a really important part. They also talk about transport and protocol separation, so you can use TCP and UDP pieces inside of async IO to implement higher level protocol elements. And then essentially it's paving the way, and migration is an important concern here, but it's paving the way to migrate from people who are using callbacks or maybe in some cases future-based yielded generators into what will become the full native coroutine. So there's a variety of utilities inside of it. I'll use a couple of them later, but you can also combine them to form hybrid library. Try that one more time. You can combine them to form hybrid libraries. So like Tornado is one that I really like their testing interface for, but I might be using it around maybe an IRC client that I wrote in async IO's base TCP implementation. So now I can be unit testing in one framework while implementing in another one. This is a big thing that came out. In fact, Glyph, who's the guy who does a lot of work with Twisted, responded to it directly with a blog post in 2014. Tornado, Twisted, these aren't dead. They are still fundamental. Hopefully you're sort of picking up on that. All async IO does is give us a path forward and actually increases the potential for competition because you don't have to go and implement every database driver out there if you introduce some new concept somewhere in the asynchronous stack. So the only reason they would be dead is if they can't compete, and that's all good for all of us, right? Everybody, the libraries, frameworks, protocol implementations, et cetera. So async IO introduces a couple different concepts: loops, futures, tasks. So an event loop we talked about, that is usually an abstraction of KQ, epoll, select. So I always forget the Windows one, but each platform has their own event loop, like I was talking about before. An event loop in all these systems, and now built into async IO abstracts that. So you just construct an event loop, it figures out the right thing to use for your system, the most optimized piece, and it runs that, and it exposes a sane interface on top of that. And then it's in charge of scheduling, executing, continuing, canceling, et cetera, the coroutine objects. And here when I'm saying coroutines, I mean everything from callbacks all the way out to the first class coroutines that you saw in Tim's talk that I'm going to talk about in a minute. A future is an object that encapsulates an eventual result, right? For those of you who haven't worked with futures before. And so what that means is the result could just be a value. The string that I got back from my receive socket call, that's a eventual result, right? That would be wrapped in a future. And the same thing, if that send or read call resulted in an exception, the socket closed or whatever, then that exception could be encapsulated inside of a future, passed where it needs to go, and then raised in the right context. And then finally, a task is a subclass of future in async IO, and it's it wraps it to provide some scheduling and tracking of those awaitables on top of some of these event loops. So not going to go much deeper than that. There's a lot of good stuff on these, but that's just base concepts when you're working with async IO. So here is a permutation of the server. Now we're going to be using a couple things that I've talked through. We've got yield from statements in here, right? So we've got sub-generator delegation. We've got async IO in a couple places. I'm using the async IO loop, and the loop gives me this create task function, so I can put a coroutine on the task loop or the event loop and say, go run. I don't need to track your result because it's going to run in parallel. But you also have things like loop socket receive. I pass in a socket object, the buffer size, just like you saw before when I said socket.receive with the buffer size and got the data on the other side. Works the same way. Now it's on a standard portable event loop. And then over here I'm just showing you that it's slightly different in that I'm using the async IO event loop, and I'm using loop run until complete, which you saw in Tim's talk. There's also run forever and a couple other options in there, which I actually have to use later. If you're noticing, though, that there's a lot of like decorators on all of the methods there inside of it. So if you saw, every one of these has to be identified. You saw it in my code earlier. Async IO.coroutine, async IO.coroutine. What happens if you don't put that on there? It's just a normal generator. It may not be wrapped. The futures may not be wrapped. They may never be handled. And you may never know that they weren't handled properly. So this is a great, we're moving really far forward in making something that's easy to reason about, but it can still be a little bit of a pain to understand what's going wrong, when futures get lost, where exceptions, there's still some improvements that we can make to exceptions and where those occur. So, and some of the problems with that. And now we get to the main point, which is native coroutines inside of Python. So we've come a long way, and we've improved a lot along the way, but now, based on the last mile learning, it turns out that yield from and this sort of slightly different view of a generator is not as useful as just taking the lessons from generators and turning it into a native concept itself. It's still built on top of that generator concepts, but it is not a generator. It now has async and await. It is a coroutine, a types.coroutine object inside of the system. And so establish a common, easily approachable mental model of asynchronous programming, which is exactly what we talked about at the beginning with coroutines. They give you another model, a way of reasoning about concurrent tasks. So that was PEP 492. And I'm calling out specifically, there's another part in that PEP, which I think is key for us as Python folks who want to see the community grow and all that. This is acknowledging that to keep Python relevant and competitive in a particular area, right? This is networking and IO-driven, event-driven operations, but to keep us competitive, we have to acknowledge that these are real challenges we need to solve inside a language, and that's why they introduce native coroutines, right? It's an important area of growth. Yep, and they call it that other languages have adopted or are planning to adopt similar features. So, available in Python 3.5. little side note, if you read my talk description, I don't know what I was thinking. I wrote native coroutines became like a part of the language in 3.6. That is wrong. It was 3.5. But in 3.6, there were a little bit of additional pieces. So in 3.5, you've got native coroutines. You've got async and await keywords. It is unique from generators, even if it builds on the same concepts. And I find the keywords, you're seeing probably a theme, I like the explicitness of them while still remaining that intuitive sort of blocking style. So await and async keywords like I talked about, types.coroutine like I talked about. You also have the double under await method that you can introduce if you want to create your own awaitable objects that work in sort of like the futures tasks system. And then you've got familiar things like asynchronous for loops and asynchronous with contexts. And so those function like you would expect, but in the event that your with context needs to do some operations before setting up the context, you have that. If you need to be asynchronously pulling off of an iterator, you can now implement that. And I'll come back to that in just a moment, the async for, because there was a little bit of limitation in Python 3.5 when they launched it, and they fixed it in Python 3.6. But all those should be fairly familiar concepts, and now they work in an asynchronous model. And you get rid of all those decorators, unless you're migrating code, in which case you might still need some decorators and things to map between yield from statements into other places. But largely, you get to get rid of all those decorators. You didn't see any of those in Tim's talk. Right? I'm not missing anything. Okay, yeah. Exceptions make even more sense when you see them. And the last 2 points are big ones for me. When you use await and async in the wrong method, you actually get syntax errors when you try to run it. So if you get unit tests to just import your code, now you know you jacked up the method that you were trying to, the coroutine that you were trying to implement as a syntax error, which you don't really get from yield froms and those things. The decorator and yield from weren't communicating with each other. And then you get runtime warning for unused features, which is huge. Like I was saying before, lost futures is a real thing, right? And we're not talking about financial markets here. Lost futures, they will cause clients to pause. You can't recreate the behavior. It all happens in production. You have no idea what happened because it's silent errors. Now, if a coroutine there's actually a couple different objects, can't remember, but if they're garbage collected without being awaited somewhere, it will throw a warning in your code. Great. That helps you understand that you've got some stuff that you're not handling somewhere. So here is, remember we talked at the beginning with the blocking server. Here is now same thing. Actually, I'm using a non-blocking server now, like the callback. But this is, you can tell this is like half the length of the callback code and does almost all the same stuff. I'm going to call out a little bit in a minute. But I'm still manually opening the sockets and wrapping all of that with the lower async IO pieces. But you see async and await. Right? Much, much more simplified code. And we can actually make it even simpler if I don't go and create my own sockets, because now you get TCP sockets and things like that inside of async IO. So now I can just pass in the IP that I want and the port that I want, and async IO will start the server for me, and it will handle all the TCP setup, non-blocking, and event listening, and now it's good to go, and I pass in, it's a callback, but it's fine here. I need to run an individual coroutine for every client anyway, because I'm going to have lots of those in parallel. So it's fine that I call out, here's my handle client coroutine, which is an asynchronous method. It gets a reader and writer, so now I'm not even messing with the lower level client socket. I just get these things that are already wrapped, and I say, await, I want to read the buffer side, parse that JSON RPC, and then send back a result to client. This is, has all of the benefits, in my opinion, of the blocking synchronous sort of implementation at the beginning, but now it's scalable. It will handle any number of clients. Obviously, any number is a thing, but it scales much better. Now we still have a bit of a problem here in that if you're talking about a bidirectional, you want to implement a bidirectional protocol, then we can't have this request response tie, right? Like, so we're looping forever, but we're reading and then we're responding. Well, what happens if I want to trigger based on an event over here? I need to have access to this writer. I've got to go build some context of sharing that writer. That's not going to work. But we're talking about coroutines. The whole point is that there are these composable units of work that you can run in parallel or concurrently. So we can tweak it a little bit. Oh wait, is this the right thing? Oh, that was just showing you. I should have gone here, like synchronous blocking, new stuff. So you can see the length is about the same. All right, parallel read-write is, now I've got 2 additional coroutines. And yeah, it looks slightly more like the callback-oriented code in that you've got a number of methods, but it's not callbacks. It is coroutines, and you're scheduling these individual ones. So we start at the server, and then down here on the handle client, I don't know why I didn't put that up there, but on handle client, we still get the reader and writer. Instead of immediately going into a loop where we read and write on it, I'm just scheduling the read coroutine and the write coroutine. And now, I'm not really doing much valuable with this, but you could easily see how you could iterate on this code and add in maybe a middle layer between the read and write. So you have an in queue and an out queue, and all the JSON RPC stuff gets dropped into an in queue and then parsed by something that pitches off the individual methods or calls out to external services or whatever you need to, and then it writes to the out queue, which goes out to the client, right? And so now we have parallel reading and writing, bidirectional protocol support, not that I'm doing anything valuable with it, but you have that inside of the server. It scales based on the event loop, and it looks largely like your synchronous and blocking code. So that's great. Oh, this is a little bit larger for those of you who couldn't see it before. These are just my two simultaneous read and write coroutines, if that makes it a little easier to read. And you see there's this queue that I constructed earlier, which is just async IO gives you a queue that you can wait on the put and get operations. So that's coroutines and what it can do to your code base. The last little evolution of Python point is in 3.6, they introduced async generators. So if you remember before, I said you've got the double under iter and async for and async with, but you don't have a yield statement, an asynchronous yield operation anymore, right? You have to, it sort of goes all the way back to iterators. Now you got to implement your own, stack, context, whatever, inside of your asynchronous coroutine functions. So there's no equivalent concept for the asynchronous iteration protocol. And they actually call back to the PEP that I was showing you earlier when they introduced yield and generators in the beginning. Now they're saying, we need this inside of our coroutines as well. So, and you have pieces of it. Oh, I forgot to put that in there. Yeah, so now you're stacking, right, generators on generators on generators. But, I don't think that everybody's going to necessarily jump in and be like, yeah, I need my yield and yield from inside of my coroutine. But if you do, if your workflow is that sophisticated, then you now have that yield inside Python 3.6. You have a iterator and a next. You remember earlier it was iter and next were methods. You have a send, a through, or just I think it's a through. I think I misspelled that. And a close on these asynchronous generators, just like you had send, throw, and close on normal generators. And inside of now the body of your coroutines, you have an await keyword, you have yield, and you have return. So you have sort of a full concept there. So I'm not going to show, I didn't show like a permutation of the socket server that I made before because I didn't really, honestly, I don't have a great compelling use case in that model for why you would need a yield statement inside of my coroutines, but you could come up with some interesting ones. So, closing thoughts. There's a whole bunch more that I could have talked about. In fact, I gave a longer version of this a year ago at Austin Python. It obviously was a lot more limited in some cases, but I talked about things like testing and good practices around how you handle loops and all of those kind of things. So I'm just going to call it a few things. Supporting explicit loops in your function signatures. Now what I'm talking about here is not the code I was just writing, but when you go and write a driver, when you're writing your own wrapper for your own service, asynchronous SDK or something like that, you need to be thinking about passing in loops because people have these different loop concepts, right? They have the async IO loops. There's a lot of tools in there to use the one that happens to be in the current, in the memory at that moment because they all have like this .instance global or some similar pattern, and those can work okay, but especially when you start talking about testing and migrating your code around, if you're not passing around loops, it can be a problem. So take that or ignore that. That's just a piece of advice for me, especially for those of you who are writing drivers or wrappers around other things. Make sure you handle the result case. That one goes without saying, but if you're implementing futures, talking about futures, make sure you're calling that result. You'll get warnings in other places if you don't handle them, but that's an important one. The next line, hopefully you sort of got from the talk, but in general, as you're migrating code or whatever, async and await is obviously the gold standard, but you can iterate from callbacks to yield from statements, especially if you're going from a Python 2 project into, like you're finding your way to Python 3.5 or 3.6, then yield wrappers and then eventually 3.3 yield from wrappers can get you stair-stepped into a method of using async and await. wrap those hybrid futures. You saw that in Tim's talk, where he took a future that was returned from an asynchronous I/O object and he wrapped it with a tornado future. When you're using different libraries, sometimes you're going to need to wrap those futures. I say you don't have to standardize necessarily on one testing framework like I talked about before, but you are going to want to standardize on a testing framework concept, right? Like I said, I really like the tornado method, but when you're testing, a lot of times you don't necessarily have the ability, to spin up, the event loop like you'd want to, and so there are a lot of helpers in some of these that make your tests easy to reason about, and we'll do a lot of that spinning up, running synchronously, return a value that you can run your assertion on. So find one, standardize on it, don't try to go and necessarily roll your own, I guess is the biggest point there, because there's a lot of good ones out there. And Docker is your friend because Python 3.6 isn't everywhere. So anyway, other implementations and concepts, if you like just coroutines as a concept, there's a lot of cool concepts in some C implementations. There's boost coroutines. Node now has async and await. I believe in ES 2017. I don't know if they're doing years or numbers anymore, but I think they have that now. Go routines, for those of you who use Go, you'll find some parallel concepts there. Ruby fibers, etc. And then continuations in the actor model and some functional concepts are cool permutations of coroutine type objects. And then these are all in a file on the GitHub, but here's just some interesting things to go look up. David Beasley's coroutine guide, that's an old, I say old, 5-6 year, maybe longer, Python guide to building out coroutines in generator type worlds. And so it's a nice rundown of those things. Async IO libraries, that's all as far as they've made updated things like Tornado and Twisted, but also AIO, HTTP, AIO, Redis, all of those things. A couple of links there to coroutines implemented in C and some really fun, sketchy ones that are playing around with things. Yeah, a couple other things. And then this is just a fun one. So when Guido was digging into, I think, async IO and implementation and understanding Tulip and all of those things when he was writing it, he actually, on the Twisted mailing list, I think it was, he went through and gave this really long description of how Twisted deferreds work, which is essentially future concepts, but they're pretty sophisticated. And so it's great because it gives you a deep understanding of Twisted's nature, but it also helps you understand why certain things function the way they do now. So that's it. Yeah. Mountain scenery. So, any questions? Oh. Any questions? That makes it easy. Okay. Thank you.